Hello everyone, so in this video I am going to discuss previous year's questions from the chapter capacitors, which I have categorized as problem type. So if you watch this video till end, you have the idea what different types of question which can be asked in JEE Mains. And I have done the same activity for others chapter. If you have not watched the videos from other chapters, please do so. So the link for those videos I have shared in the description. Now let us see who will get benefited from these videos. So if you know basics but you are unable to approach numericals, so this video is for you. And if you have some basic NCERT level knowledge but you want to write JEE Mains exam but you are not good with numerical part, so this video is for you. And you have done coaching, still your problem solving is not clear to you, so this video is for you. How to watch this video effectively? First you have to revise the short notes which you have prepared for this chapter. Then you have to write down the important information that you come across in the video. And then whenever I discuss an illustration, first you have to pause the video, try to solve the illustration on your own. If you're not able to solve, then you can watch the solution. Right? Now again, this chapter is very important because around 1 to 2 questions can be asked in JEE Mains. Right? And this is the syllabus, so there is no change in the syllabus with respect to the last year. And this is the mind map where I have mentioned all different areas which you have to focus. Now let us jump to the problem types. The very first problem type, and it is based on spherical capacitors. So let us see the question. A capacitor of an isolated conducting sphere of radius r1 becomes n times when it is enclosed by a concentric conducting sphere of radius r2 connected to the earth. The ratio of their radii r2 by r1 we have to calculate. Okay, so first of all we should know what is the formula of the capacitance in case of an isolated conductor, spherical conductor. So if we have an isolated spherical conductor of radius r1, then the capacitance will be given as 4 pi epsilon naught times r1. Now what we have done, this capacitance becomes n times when it is enclosed by a concentric conducting sphere of radius r2. Okay, so if we enclose this with a spherical shell of radius r2 and it is grounded. In this case, the capacitance, now we have a pair of concentric shells, it will become 4 pi epsilon naught times r1 r2 upon r2 minus r1, right? So these are the typical formulas that we use in case of spherical capacitors. Now we have given C1 becomes, or C2 is nothing but n times of C1. So we can say 4 pi epsilon naught times r1 r2 upon r2 minus r1 is equals to n times 4 pi epsilon naught times r1. Now if we remove the constant factor, so 4 pi epsilon naught will get cancelled out, 1 r1 will get cancelled out, and we have to find r2 by r1. So if I divide left hand sides, numerator and denominator with r1, we will get r2 by r1 upon r2 by r1 minus 1 equals to n. And let me take r2 by r1 as x. So we can say x upon x minus 1 will be equals to n. And from this we can say n is equals to n minus 1 times x. So x comes out to be n upon n minus 1. So option A is the right answer. Now let us see the next problem type, and it is based on series and parallel combination of capacitors. Let us see this question. 3 capacitors of capacitance 25 microfarad, 30 microfarad and 45 microfarad are connected in parallel to a supply of 100 volt. When capacitors are in parallel, the equivalent capacitance is nothing but the sum of all the capacitances. So here when they are connected in parallel, C equivalent, let me call this as C1, will become 25 micro plus 30 micro plus 45 micro, which comes out to be 70, that will be 100, right? 100 microfarad. Energy stored in the above combination is E. So energy will be half C1 V square, and V is nothing but 100. So that will become half in times 100 micro times 100 square, which is nothing but 1 by 2 joules, because micro is 10 raised to power minus 6. When these capacitors are connected in series to the same supply, the stored energy becomes 9 by X times E. So in series combination, the equivalent capacitance will be 1 by 20 micro plus, so that is 25. 1 by 25 plus 1 by 30 micro plus 1 by 45 micro. Right, so in this case, what is the LCM? So we have 300, and this, let us take it as 900, right? 900 micro. So it comes out to be 3, and we have 156 plus 30 plus 45, so that will be 20. So 1 by C2 comes out to be 50, and this will be 86 upon 900 micro. So C2 comes out to be 900 upon 86 microfarad. So the energy is given as 9 by X times E, which is 1 by 2, and that is equals to half C2 times V square, so that will be 100 square. Now we have to find the value of X from this equation. So this will give us 100. Now this will cancel out with micro, and this 2 will get cancelled out with 2. So X comes out to be 86. Right, so 86 is the answer of this question. Now let's see one more illustration. A capacitor is made of a flat plate of area A and a second plate having a stair-like structure as shown in the figure. If the area of each stair is A by 3 and the height is D, the capacitance of the arrangement is. So this stair-like structure is equipotential, right? It is having a constant potential on this surface, and this plate will be having a constant potential. So we want to find the potential between, if we call this point as B and this point as A, so we have to find the capacitance between A and B. So what we can say, basically we have 3 capacitors which are in parallel, right? So this is first capacitor C1, this is second, and this is third capacitor, and C1 is epsilon naught times A by 3 divided by the distance between the plate, which is D, and C2 is epsilon naught times area A by 3 divided by the distance between the plate. Now the distance between the plate will be 2D. Similarly, C3 will be epsilon naught times A by 3 divided by 3D. Now these 3 capacitors are connected in parallel, so C equivalent will be sum of these capacitances, C1 plus C2 plus C3. So epsilon naught A by 3 by D will be common. So 1 plus 1 by 2 plus 1 by 3. So LCM will be 6. So 6 plus 3 plus 2 times epsilon naught A by 3D. So which comes out to be, so it will be 811 epsilon naught A divided by 18D. So option 2 is the right answer. Let us see the next question. The equivalent capacitance between points A and B in below shown figure will be. So we have to find the equivalent capacitance between A and B, and we have given 6 capacitors. So whenever we have a large number of capacitors, first of all we have to figure out whether we have any short circuited capacitor or not, and then we have to look for the series and the parallel combination, right? So if you look at these 2 capacitors, They are in series, but their ends are connected with a connecting wire. So it means it's a short circuited capacitor, right? So if it is a short circuited, you can remove these capacitors, right? Because there will be no charge stored on these capacitors. So we can remove this. So now the circuit will look like this. So we have two capacitors, and here we have another capacitor, and this one. Right? Now we have to identify the series and the parallel combination. So what we can do, let us locate the equipotential points. So this point is A, so this is also A, because these 2 points are connected with a connecting wire. And if this point is C, then this point is also C, because these 2 points are connected with a connecting wire. Now show the 3 equipotential points which we have marked in the diagram. So A, then we have C, and then we have B. Now, how many capacitors are connected between A and C? So this is the first capacitor, this is the second capacitor, this is the third capacitor. So there are 3 capacitors which are joined between A and C. So there are 3 capacitors in parallel. 1, 2, and that is the third capacitor. And between C and B we have only one capacitor. Okay, and all these capacitors are identical. Let me call this as C only, right? All capacitors have the same capacitance, and C is 8 microfarad. Now these 3 capacitors are in parallel, so it will be 3C. Now 3C and this C are in series, so we can say 3C times C divided by 3C plus C will be C equivalent, which will be 3C by 4, and C is 8 microfarad. So it comes out to be 6 microfarad. Okay, so 6 is the answer of this question. Now let us see the next problem type, and it is based on system of parallel plates. 4 identical rectangular plates with length 2 cm and breadth 3 by 2 cm are arranged as shown in the figure. The equivalent capacitance between A and C is X epsilon naught by D. The value of X is right. And this X is in square meter, right? A square centimeter. Okay, so this thing you have to keep in your mind. This X is in square centimeter. So let us see how to find the capacitance between point A and C. So since we are finding the capacitance between A and C, so we are connecting a battery like this. Okay. And B and D are joined together with a connecting wire, so we can say the potential of B is same as potential of D. So I am calling this, if this is B, then I can also call this as B. Okay, because they are equipotential. Now let us show the equipotential points. So we have A, so I'm calling this plate as A. Then we have B, and then I'm calling this plate as C. Right? Now how many capacitors we have between A and B? So this is the capacitor between A and B. So let me call this as C. Now how many capacitors we have between B and C? So this is one capacitor, and this is another capacitor. So we can show 2 capacitors in parallel. And we have to find the capacitance between A and C. Right? Now this is also C, this is also C, right? And C is nothing but epsilon naught times L times B, that is the area of the plate, divided by the distance between the plate, which is D. Okay, now this capacitor is in series with the combination of these 2 parallel capacitors. So this will be 2C. So we can say 2C times C by 2C plus C will be C equivalent, and it comes out to be 2C by 3. And 2 by 3, and C is epsilon naught times LB by D. L is 2 and B is 3 by 2. So it comes out to be 2 times epsilon naught by d. So we can say x is 2. So the answer will be 2 in this case. Right, so now let us see the next problem type, and it is based on the charging of capacitor. Let us see the question. A 16 ohms wire is bent in to form a square loop. So we have given a wire and we are forming a square loop. So if it is 16 ohms wire, and we know that in case of a uniform wire, the resistance is proportional to the length. So each side will be having a resistance of 4 ohms. A 9-volt battery and internal resistance 1 ohms is connected across one of its side. So we are connecting a battery which is having some internal resistance. Internal resistance is given as 1 ohms and the EMF is given as 9 volts. If a 4 microfarad capacitor is connected across one of its diagonals, the energy stored by the capacitor will be x by 2 microjoules, and we have to find the value of x. So let us see, and we are connecting a capacitor along the diagonal. This is 4 microfarad. Now when we have given a circuit like this, it means they are asking about the steady state condition. So what is the steady state condition? When the capacitor is fully charged. Okay, so in steady state, capacitor is fully charged. So if the capacitor is fully charged, we can treat capacitor just like a open switch. So the equivalent circuit will look like this. Right? So this branch has a resistance 4 ohms, it is having a 4 ohms, it is having a 4 ohms, here we have 4 ohms, right? And this is 1 ohms and this is 9-volt battery. Now if you want to find the energy stored in the capacitor, we should know what is the potential drop across the ends of the capacitor. So what is the potential difference? So for that we should know the current in each branch. So first let us find the current supplied by the battery in this case. Now these 3 capacitors or resistors, they are connected in series. So it will be nothing but 12 ohms. Now this 12 ohms is in parallel with this 4 ohms. So we can say 1 by 4 plus 1 by 12 will be equals to 1 by say r prime. So it will be 3 4 by 12 1 by r prime. So r prime comes out to be 3 ohms. Now this r prime is in series with this 1 ohm. So R equivalent will be 1 plus 3, so which comes out to be 4 ohms. So the current supplied by the battery will be 9 by 4, so that will be 2.25 amperes. Now this is the current 2.25. Now this 2.25 ampere current will split up into 2 branches. So let us take this branch. Let us, this current is I1. And we know that when we have 2 parallel resistors, the current will divide in the inverse ratio of the resistance. So I1 will be equals to 9 by 4, that is the total current, times 4 divided by 4 plus 12, where 4 is the resistance of this branch and 12 is the resistance of this branch. So this comes out to be 9 by 16. So I1 is 9 by 16, and we have to find the potential difference between these 2 points, because these are the ends of the capacitors. So if this is A and this is B, then we can say VA minus VB will be I1 times 4 plus 4. That is the resistance between A and B. I is 9 by 16 times 8. So it comes out to be, this will be 2, so 9 by 2. Now that is the potential difference across the capacitor, and if we want to find the charge, so this is the potential, and we have to find the energy stored. Okay, right. So the energy stored will be half CV square, and half C is 4 microfarad and V is 9 by 2, so that will be 81 by 4. So 4 will get cancelled out. So the energy stored will be 81 by 2 microjoules, and we have given energy stored as x by 2 microjoules. So if we compare, x comes out to be 81. Okay, so the answer will be 81. Right, so now let us see the next problem type, and it is based on work done by battery and heat dissipation in charging a capacitor. So let us see one of the illustration. So here we have given an electrical circuit. A battery is connected to pass 20 coulomb of charge through it in a certain given time, and the potential difference between the two plates of the battery is maintained at 15 volts. The work done by the battery. So the work done by the battery is defined as the product of charge supplied and the potential maintained across the battery. So in this case it will be EMF. Let us take it as EMF, right? So charge supplied is 20 and the EMF is 15, so it comes out to be 300 joules. Okay, now let us see the case when we are charging a capacitor. So let us say there is a battery of EMF E and we are charging an uncharged capacitor with the help of this battery, and we need to find how much will be the heat dissipated in charging this capacitor. So let us, the capacitance is C, and when we close the switch, then the charge on the capacitor will become C times E, right? So that is the charge. So work done by the battery will be, the charge supplied by the battery is CE, and the EMF of the battery is E, so work done by the battery is CE square. Now what is the increase in the electrostatic potential energy of the capacitor? It will be half CE square. So when we have an uncharged capacitor and if we charge that capacitor, then half of the work done by the battery will be dissipated in the form of heat energy. So here the heat energy will be work done by the battery minus change in the potential energy of the capacitor. Okay, so this formula you have to remember. And suppose if we have this scenario, so there is a battery and we have a capacitor which is already charged. So this is positive plate, this is negative plate, and on this the charge is CE. Here we have minus CE, and this battery is having EMF 3E. So when we close this switch, the final charge on the capacitor will become 3CE because this capacitor has a capacitance C. So the charge supplied by the battery will be 2 times CE because final charge is 3CE and initial charge is CE, so the charge supplied by the battery will be 2CE. So work done by the battery in this case will be 2CE times the EMF of the battery, so it comes out to be 6CE square. So what is the increase in electrostatic potential energy of the capacitor? So let us find that. So final charge we know and initial charge we know, right? And the potential, so we can say it will be Q square by 2C, right? So we can use that formula. So it will be 3CE square by 2C minus CE square by 2C. So this comes out to be 9 by 2 minus 1 by 2 CE square. So which comes out to be 4 CE square. Now if you want to find the heat dissipated in this in the charging of the capacitor, so delta U or delta H comes out to be work done by the battery minus delta U. So work done is 6 CE square minus delta U is 4 CE square. Now this comes out to be 2 CE square. Now in this case, it is not 50% of the work done by the battery, right? But in this case, delta H is equals to delta U. But here delta H is not equals to delta U. So you have to remember this. When the capacitor has some initial charge, then the heat dissipation is not same as the change in the electrostatic potential energy. The next problem type, and it is based on like when we connect two capacitors together, then what should be the final potential of both the capacitors, then or what will be the final charges on the capacitor, and what is the change in the electrostatic potential energy of the system. So these types of question I'm going to cover in this type. So let us see one of the illustration. uh, Two identical capacitors having same capacitance C, one of them is charged to the potential V and the other to 2V. So let me take this as V2 and this one as V1, and both have same capacitance. So C1 is equals to C2 is equals to C. V1 is 2 times 2V and V2 is V. The negative end of both the capacitors are connected together. When the positive ends are also joined together, the decrease in energy of the combined system. So let us see. So we have given two capacitors. Let us say this is the negative plate. This is the positive plate of first capacitor. This is the negative plate and the positive plate of the second capacitor. And their negative plates are joined together. So this one is C, this is also C, and let me take this as 2V, which is say V1, and this is V2, which is given as V. Now we are joining their positive plates as well. So when we join this, right? So what will happen in this case? There will be decrease in electrostatic potential energy, right? And that energy will be dissipated in the form of heat energy. So you can remember this formula. So the energy which is being dissipated will be given by half C1 C2 upon C1 plus C2 V1 minus V2 whole square. Okay, but suppose if we are connecting their positive plate with the negative plate, in that case this negative will be replaced with the positive sign, and then you can apply the formula. So here let us put the values. So half C square upon 2C, and V1 is 2V minus V square. So this comes out to be C by 4 times V square. So option 1 is the right answer. So the next problem type is insertion of slab in a capacitor which is connected with a battery. So let us see a typical question. A parallel plate capacitor with plate separation 5 millimeter is charged up by a battery. So we have given a parallel plate capacitor and the spacing between the plate is 5 millimeter. And we are charging this capacitor with the help of a battery. Let us say the EMF of the battery is E. So we and the capacitance for this capacitor will be epsilon naught times area of the plate divided by the spacing between them, D, where D is given as 5 millimeters. Now it is found that on introducing a dielectric sheet of thickness 2 millimeter while keeping the battery connection intact, the capacitor draws 25% more charge from the battery than before. So the final charge on the capacitor after inserting a dielectric slab of thickness 2 millimeter, it stores 25% more charge than before. So now what we can do, if we insert a slab of thickness 2 millimeter, the new capacitance, let me call this as C prime, will be given by epsilon naught times A divided by thickness of the slab, that will be 2 millimeter, divided by its dielectric constant, which is given as, let us take it as K only because we have to find the value of K, plus the spacing, the width of the spacing which contains vacuum will be 5 minus 2, that will be 3 millimeters, divided by dielectric constant of the vacuum, that will be 1. So that is the new capacitance. And when the battery is intact, battery's main purpose is to maintain the potential difference across the capacitor. So potential difference will not change in such cases. So the final charge, initial charge is epsilon naught times A by D times, or let me put D as 5 millimeters. Times E, right? And this is, let me call this as initial charge, and the final charge is epsilon naught A divided by 2 millimeter by K plus 3 millimeter by 1, and this final charge is 1.25 times of initial charge that is given in the question. So let us put the values in this equation. So we can say epsilon naught A, okay, and we have to multiply this with V also, right? So epsilon naught A times EMF upon 2 by K plus 3 by 1 is equals to 1.25 can be written as 5 by 4 times epsilon naught A times E by 5. So this 5 will get cancelled out. This will get cancelled out. So we get 2 by K plus 3 equals to 4. Now from this 2 by K comes out to be 1. So K comes out to be 2. So the dielectric constant of the slab is 2. So that is the answer of this question. Now let us see the next problem type, and it is based on the insertion of slab inside the capacitor which is not connected with the battery. Right, so let us see a typical question. A parallel plate capacitor of capacitance 12.5 picofarad is charged by a battery connecting between its plate to a potential difference of 12 volt. So we have given a parallel plate capacitor and the capacitance is 12.5 picofarad, and it is charged with the help of a battery of EMF 12 volts. So due to this battery, it will acquire some charge, right? And the initial charge on the capacitor will be C times V, and it will be 12.5 pico farad times 12. So this will be 25 by 2 times 6 pico coulomb. So that comes out to be 150 pico coulomb. So that is the initial charge on the capacitor. The battery is now disconnected, and the dielectric slab of dielectric constant 6 is inserted between the plates. The change in its potential energy after inserting the dielectric slab. So we have to find the change in energy. So for that, let us and when there is no battery connected, the charge on the capacitor will not change because there is no conducting path for the charge to move. So in such cases, when the battery is not connected, you have to keep charge same. So we can say the final charge will be same as 150 picocoulomb. But as you insert the dielectric between the plates of the capacitor, the capacitance will increase by the factor K. So we can say the new capacitance C prime will be 12.5 times 6 picofarad, right? So that will become 25 by 2. So this will be 375 picofarad, right? So that is the new capacitance. So initial potential energy will be Q square divided by 2C, and the final, like after inserting the dielectric, it will become Q square divided by 2C prime. So we have to take the difference. As C prime is less than C, so the energy will decrease, right? So so if I do initial minus final, that comes out to be Q square by 2, 1 by C minus 1 by C prime, and Q is 150 pico, 150 pico square by 2, and 1 by C is 12.5 picofarad, minus 1 upon 75 picofarad. Okay, so let us simplify this. So this can be written as 150 times pico square divided by 2, and right, so if we multiply this with 25, and this comes out to be 6, right? If I multiply this with 6, so 6 times 12.5 is 75. So we get 5 upon 75 pico. So this pico will get cancelled out. This will give us 15. This will give us 10, and this will be 75. So we are getting 750 pico joules. So which is 750 into 10 raised to power minus 12 joules. So the answer is 750 for this question. Right, so let us see the next problem type. Not it. It is again based on the same problem type. Two capacitors of capacitance 2C and C are joined in parallel and charged up to the potential V. The battery is removed and the capacitor of capacitance C is filled completely with a medium of dielectric constant K. The potential difference across the capacitors will now be. Okay, right. So we are charging both the capacitors with the same battery. So this is the circuit diagram. Potential is V, this is 2C and this is C, right? Now due to this battery, the charge on the first capacitor will become 2CV and this will be minus 2CV, and here it will be CV and this will be minus CV. Now we have disconnected the battery. So now we have two capacitors which are charged and they have same potential. Okay, now we are inserting a dielectric slab between the plate of the capacitor C, and the dielectric constant is K. Now due to this dielectric slab, the capacitance of the right capacitor will increase. Okay, so now there will be redistribution of the charge, and the charge will move till both the capacitor will again acquire common potential. So if you look at the charge on this system, we can say it is 3 CV, right? So 3 CV is the total charge on the system. Now this total charge will be distributed in these two capacitors. And when the charge flow stops, both will acquire same potential. So we can say Q is equals to CV. For same potential, charge will charge will be proportional to the capacitance of the capacitor. So we can say the final charge, say on the right capacitor, will be, let me call this as Q2. It will be total charge 3 CV on the system times K times C divided by Kc plus 2C, right? So that is the final charge. And if you want to find the final potential of the capacitor, you can divide the charge with the capacitance. So this will be Kc, right? So that will give us the final potential. So which comes out to be, so this Kc will get cancelled out, and we have 3V times C divided by K plus 2 times C. So 3V upon K plus 2 is the answer. So option 3 is the right answer. Now let us see the next problem type, and it is based on the force between plates of the capacitor. A capacitor of 10 microfarad capacitance whose plates are separated by 10 millimeters through air, and each plate has an area of 4 square centimeter, is now filled equally with two dielectric media. K1 is 2, K2 is 3 respectively as shown in the figure. If now new force between the plate is 8 Newton, the supply voltage is, so we have to find the supply voltage, and if we want to find the force between the plate, the formula will be given as Q square by 2A epsilon naught, where Q is the charge on the plates. But this arrangement, okay, let us first find the original capacitance. So 10 microfarad is epsilon naught times area A divided by D, right? So this is given as 10 microfarad. And these two capacitors are connected in parallel, right? So we can say we have two capacitors like this, and they fill the space equally. So we can say this area is A by 2 and this is also A by 2, right? Let us, this is C1 and this is C2. So let us find C1. So C1 will be K1 times epsilon naught times A by 2 divided by D. So which will be 2 by 2 times 10 microfarad. So it will be 10 microfarad. And C2 will be K2 times epsilon naught A by 2 divided by D. So that will be 3 by 2 times 10 microfarad. So it comes out to be 15 microfarad. Right, so we got the capacitances. Now on this plate the charge is, let us say, q1. Here we have minus q1. On this plate the charge is q2. On this plate it is minus q2. Now let us find the force of attraction in both the capacitors, and then we can simply add the force of attraction, and that will give us the desired result, right? So we have to find the supply voltage, and the total force is given as 8 Newton. Let us say for the first capacitor the force is F1, and for the second capacitor it is F2. So F1 can be written as Q1 square upon 2A epsilon naught. And A in this case, if you look at the area of the first capacitor, it is A by 2. So I will write A by 2. So this will get cancelled out. And similarly, F2 will be Q2 square upon 2 times A by 2 times epsilon naught. So 8 Newton is given as F1 plus F2. So 8 is equals to Q1 square plus Q2 square times 1 by epsilon naught times A. And what is Q1? So let us first find Q1. Q1 is C1 times the voltage, right? And Q2 is C2 times the voltage. And C1 is 10 microfarad. And C2 is 15 microfarad. So let us put the values. Plus 15 microfarad times V square, and then we have 8 epsilon naught times A. So 8 times 8.854 into 10 raised to power minus 12 times area is given as 4 square centimeter. So that will be 10 raised to power minus 4 divided by 10 raised to power minus 12, right? I'm taking this, right? 10 raised to power minus 12 equals to 100 plus 225 times V square. So this will be 8 times 4 times 8.854 divided by 325 times 10 raised to power minus 4 V square. So here we have minus 6 minus 12. Let me again check. 8 area is 4 and D value is not okay, right? Okay, right. So let me just simplify this. So 8 times 4 times 8.854 divided by 325, right? So I'm getting, so from this, by simplifying, you will get V as 9.33 into 10 raised to power minus 3. And here we have given the supply voltages dash times 10 raised to power minus 4. So this can be written as 93 into 10 raised to power minus 4 volts. And it's an integer type question, so it should be 93, right? So 93 is the answer of this question. I hope the concept is clear to you. Now let us see the next problem type, and it is based on constant dielectric, right? When we have a constant dielectric between the plates of the capacitor. A parallel plate capacitor with plate area A and the plate separation is D is filled with a dielectric material of dielectric constant 4. So this is 4, right? K is 4. The thickness of the dielectric material is X, where X is less than D. And let C1 and C2 be the capacitance of the system for X equals to D by 3 and X equals to 2D by 3 respectively. And C1 is 2 microfarad. Then what is the value of C2? Right. So when we have slabs, dielectric slabs, and their thickness, it is not completely filling the space, then we can use this formula. So capacitance will be given as epsilon naught times A divided by summation of Ti upon Ki, where Ti is the thickness of the ith dielectric slab, where Ki is the dielectric constant of the ith slab. Now in this case we can say there are two slabs, one is made of vacuum, other is made of this dielectric material. So here C1 comes out to be epsilon naught times A divided by thickness x is d by 3, so d by 3 divided by the dielectric constant, which is 4, plus the thickness of the vacuum will be d minus x, so minus d by 3, so d minus d by 3 divided by the dielectric constant of the vacuum, which is 1. So it comes out to be epsilon naught times A divided by d by 12 plus 2d by 3, and so if I multiply this with 4, so we are getting 12 upon 5, 12 upon 9 epsilon naught A by d, or which can be written as 4 by 3 epsilon naught A by d, right? So that is C1, and C1 is given as 2 microfarad. So 2 microfarad is given as 4 by 3 epsilon naught A by d. Now from this we can find the value of this vector. So it comes out to be epsilon naught A by d comes out to be this will be 3 by 2, so 1.5 microfarad. Now let us find C2. So C2 will be epsilon naught A divided by the thickness x is 2d by 3, so 2d by 3 divided by 4 plus d minus 2d by 3 divided by 1. So this will be epsilon naught A divided by d by 6 plus d by 3. So this comes out to be 2 times epsilon naught A by d. So which will be 2 times 1.5 microfarad, which is 3 microfarad. So the answer will be 3. Right, so let us see another illustration. A capacitor has air as a dielectric medium and two conducting plates of area 12 square centimeter, and they are 0.6 centimeter apart. Okay, let me just draw the diagram. Spacing is given as 0.6 centimeter and the area is 12 square centimeter. When the slab of dielectric having area 12 square centimeter and 0.6 centimeter thickness is inserted between the plates, one of the conducting plate has to be moved by 0.2 centimeter. So basically we are increasing the space between the plate. Now it becomes 0.8 instead of 0.6 to keep the capacitance same in the previous case. Right, so if C1 is the capacitance in the previous case, we can say it will be epsilon naught area, that will be 12 divided by d. D is 0.6, right? So that is in centimeter square and this will be in centimeters. The new capacitance, when we insert a dielectric slab and then increase the space between the plate, it will become epsilon naught times 12 divided by thickness. Thickness of the slab is 0.6 divided by the dielectric constant, let us take it as K, plus 0.2, where 0.2 is the thickness of the vacuum, divided by 1. And C1 and C2 both are equal, that is given in the question. So that is in centimeter square. So C1 is equals to C2. So epsilon naught times 12 divided by 0.6 should be equals to epsilon naught times 12 divided by 0.6 by K plus 0.2. So this will get cancelled out. So from this we can say 6 is equals to 6 by K plus 2. So 6 by K comes out to be 4 and K comes out to be 6 by 4, which is 1.5. So option 4 is the right answer. Now let us see the next problem type, and it is based on the variable dielectric constant. A parallel plate capacitor has a plate area A separated by a distance d. So this distance is given as d. It is filled with a dielectric which has a dielectric constant that varies as So k is a function of x, and k times 1 plus alpha x, where x is the distance measured from one of the plate. So actually what they mean, if I take a slab at a distance x and the thickness of the slab is dx, if we consider this particular slab, thickness is dx, then at this location the dielectric constant will be given as k times 1 plus alpha times x. Okay. Now if we divide this dielectric material into infinite slabs, okay, and all these slabs are connected in series, yes or no? So if we consider these infinite slabs in series combination, and dc is the capacitance of one of the slab, which can be written as kx times epsilon naught times area by the thickness, and thickness will be dx. So let us put the value of k, which will be k times 1 plus alpha times x times epsilon naught a divided by dx. Now that is the capacitance of one of the slab, and all the slabs are connected in parallel. So if you want to find the equivalent capacitance, it will be nothing but the integration of 1 by dc, right? Because they are connected in series. So this can be written as dx divided by k 1 plus alpha x times epsilon naught times a, integration of this. So this can be written as, so we can take 1 by k epsilon naught a out of the integration because it is a constant factor, and we can write 1 plus alpha x, and we can take 1 plus alpha x in the numerator, and it will become 1 plus alpha x raised to power minus 1. Now we have to integrate this, and we have given in the question that alpha d is very small in comparison to 1. So the total capacitance of the system is best given by which expression? So if alpha d is very small in comparison to 1, then alpha x is even smaller than 1, even more smaller than 1, right? So here we can use binomial approximation, so we can bring this negative 1 inside the bracket. So so 1 plus alpha x raised to power minus 1 will become 1 minus alpha x. So this will become 1 upon k epsilon naught times a 1 minus alpha x. Now we have to integrate this. So if we do the integration, it will become x minus alpha x square by 2, and the limit will be x is varying from 0 to d. So let us put the limits. So 1 upon k epsilon naught a d will be common. So 1 minus alpha d by 2. So that will be 1 by c equivalent. So c equivalent comes out to be k epsilon naught times a divided by d, and then we have 1 minus alpha d by 2. Now again you can take this 1 minus alpha d by 2 in the numerator. So it will become k epsilon naught times a by d times 1 minus alpha d by 2 raised to power minus 1. Again I can use binomial approximation, and we can remove this negative 1 and multiply this with alpha d by 2. So it will become plus. So the answer will be k epsilon naught a by d times 1 plus alpha d by 2. So option A is the right answer. So I hope now you know how to approach when the dielectric constant is not constant but it is variable. Now let us see the another problem type, and it is based on the system of two plates. Two identical thin metal plates having charges Q1 and Q2 respectively, such that Q1 is greater than Q2. The plates were brought close to each other to form a parallel plate capacitor of capacitance C. The potential difference between them is, okay, so here we have given two plates. On this plate the charge is Q1, on this plate charge is Q2. So when we bring them closer to each other, then the charge will distribute, and on the outer surfaces the charge will be Q1 plus Q2 by 2, and on the inner surface of of left plate will be Q1 minus Q2 by 2, and on this surface it will be negative of Q1 minus Q2 by 2. And when and whenever we use this formula Q is equals to CV, this charge is the charge on the facing surfaces, right? So here this Q will become Q1 minus Q2 by 2 times is equals to C times V, and we have to find the potential difference between them. So potential difference will be Q1 minus Q2 by 2C. So option C is the right answer. If you find videos of this series useful, so it is highly recommended for you to join PracBee's revision program. So in this program, we're going to cover 10 blocks in 10 weeks, and we'll give you a target of 1 chapter per day, and we'll be able to cover all relevant chapters by the first attempt of JEE Mains. And how you can join this revision program? By clicking on the link given in the description. And one more thing you can do, please drop a comment. Let us know what else we can do for you to make this series better. Thank you.